So in the context of memoization and dynamic programming, we looked at this grid path problem, which is an interesting curiosity, but it's not a particularly useful problem, you might argue, because it doesn't have much of an application except to illustrate some aspects of memoization and dynamic programming. So now let's look at some more quote unquote useful functions, right? So these functions involve strings. So you might want to look at two strings, right, and find out what is the longest common segment in those two strings. So this is called a subword. So a subword is a segment. So for instance, if I look at secret and secretary, then this is a segment and this is a segment. So it occurs as a block. So it has a subword of length 6. If I look at bisect and trisect, then isect is there in both. So this is a common subword. So it has length 5, right? If I look at bisect and secret, on the other hand, I have this SEC and I have SEC, and this is the longest common segment that is there in both. So the length is 3. And if I look at director and secretary, for instance, then I find very short things. So I find this RE, for instance, okay, or so I don't know why I said E. It's not E but EC, right? So I have EC and EC, right? So EC and RE are both of length 2. So this is the question now. The question is, if I give you two strings, can you tell me what is the longest common subword? Right? So now there is obviously a brute force way of doing this. So first let's see what the problem formally says. So I have two words. So U is of length m, and as we normally index in Python, let's assume that the positions in the string are 0 to m minus 1, and likewise v is of length n. So we have a string v with position 0 to n minus 1. Right? So what we want to do is find common subwords. So basically we want to find some sequence of length k in both of them, such that the two sequences of letters are the same. And if we find such a length k subsequence, we say they have a common subword of length k, and we want to find the largest k for which such a thing exists, right? So that's the longest common subword. So the brute force technique is just to check for every starting point, right? So for every starting point, so I want to find out whether there is a long subword starting from AI and BJ. Once I fix AI and BJ, I can find out what is the longest word that can start from there. If AI is equal to BJ, then it is 1, then I go to the next one. So I can keep scanning. I go from AI, BJ, AI plus 1, BJ plus 1, AI plus 2, BJ plus 2. I keep going so long as they are the same, right? And once I find that there is a mismatch, I stop. So from every ij, I can do a scan and try to find out how far I can go before I hit a mismatch, and then I can record that as the longest common subword starting at those two positions, and I do it for every position, and therefore I am going to find the maximum, right? So this is going to now take me m times n squared, because there are m times n positions, right? There are m copies of m choices for I and n choices for j. So for every I and j, I am going to start this calculation, and in general I am going to be scanning something which could be proportional to the length of the smaller word, right? So if I assume that m is bigger than n, then the length could be proportional to the smaller word, right? So just as a trivial example, you can see that if your sequences are like this, u is this and v is this, right? Now nobody has said that these longest common subwords are unique or something. So now for every position in u and v, I will find that there is a longest common subword of length 2. So I will actually be doing order n work for every position. So I can easily achieve this m times n squared, because my algorithm is not going to be able to look and say, oh, this is a special case, right? So I have to do it. So this is m times n squared. The question is, can we do something better than this by looking at the inductive substructure of this problem, right? So this is the theme of this these problems this week, which is problems which have an inductive structure which we can exploit and efficiently calculate. So we want to find the largest k such that for some positions I and j, there is a string of length k starting from ai and bj which are the same, right? So what we want to do is calculate for every I and j, that is what we are doing by brute force, what is the longest common word starting at I and j. So now what is the inductive structure? Well, if the position I in u is not equal to the position v in j in v, then there is no common word starting there, because right at the beginning you have a mismatch, right? So if ai is not equal to bj, the longest common subword starting at I comma j has to be 0. On the other hand, if ai is equal to bj, then I know that there is a longest common subword of at least 1. What happens after that? I go to the next letter. So if I know that there is a longest common subword starting from I plus 1, j plus 1, then this word is 1 more than that. So I can just take 1 plus the longest common subword at the next position, right? So this is the inductive structure, right? So if I can include I comma j in my longest common subword, then the rest of the subword starts at I plus 1, j plus 1. So whatever is the longest word I can get from there, plus this letter must be the longest word that I can get from here. So this is our inductive structure. Then what about the base case, right? So the base case is we are now looking at from I onwards, right? So when one of the strings get over, so remember that the indices are 0 to m minus 1 and 0 to n minus 1, right? So when I reach index m or index n, I have gone beyond the word, right? So when I basically have exhausted that word. So the base case actually comes when I am looking at the empty string on either side. So if I have the empty string on both sides, then there is no common subwords, that is 0, right? And in general, if I have empty string on one side, then again there is no common subword. So if I look at I comma n, because n is already beyond the length of v, or if I look at m comma j, because jm is already beyond the length of u, both of these must be 0, right? So these are our base cases for this problem. So what we have seen is that the subproblems are all these different combinations I comma j, right? So what we are going to do is obviously use some dynamic programming or memoization. So let's think of it as dynamic programming. So we have these subproblems of the form I comma j, and because this base case takes us from 0 to m minus 1, the length of the word, and beyond, so it's from 0 to m and from 0 to n. So I have to compute this for these m times n entries, m plus 1 times n plus 1 entries, right? So let me think of it as a table, right? So let's look at a concrete example, one of the examples we had. So we have secret and bisect, right? So bisect is u and secret is v, let's say. So each of them is of length 6, so they have legitimate position 0 to 5, and I have this fictitious position 6 where I have just written a dot which is beyond the thing, right? So now I need to find out how to fill up. So each entry here is of the form LCW I comma j, right? So this is the idea. So I need to find out a sensible way to fill up this entry LCW I comma j. So what do we know? Well, we know that there is some dependency. What is the dependency? It says that ij depends on I plus 1, j plus 1. So if I want to fill this entry, I need to know this entry. If I want to fill this entry, I need to know this entry. But what about this entry? Well, this entry doesn't have anything beyond it, right? So clearly I can start at this entry, right? And again, if I look above it, this also doesn't have anything. So the rightmost column has no dependencies. I could also do it in the bottom row. So I could do this way as well, right? But I'll do it on the rightmost column. So now what we already said is that since we are beyond the length of secret, we are beyond n, right? We should just treat this as going to be 0. Now I come to this column, and here, because at this point these two letters are the same, since in u of 5 is equal to v of 5, I get a 1 here, and everywhere else I have 0 because there is a mismatch, right? So because t doesn't occur anywhere else in that column. So now if I go to the next column, here I will find that, so I am looking at this row and this column, right? So basically this is E, and therefore, sorry, I am looking at that column. So therefore wherever I see an E but there is only one E here, I get a 1, right? Now I come to the next column, right? I am here and I am looking at for an R on the left hand side implicitly, and there is no R, right? So when I got this E, it is 1 plus the extension, but there is nothing below it, right? So I keep going. So here for instance I see that thanks to this is a 1, right? And now hopefully something interesting will happen. Now when I come here, I will find that this E and this E generate a 1, but 1 plus this diagonal is going to generate a 2, right? So I get a 2 here because I get a 1 from the fact that these two indices are both E, plus 1 coming from here, right? So I have this LCW I comma j is 1 plus LCW I plus 1 j plus 1, and then likewise here I find that S and S are the same, right? So when I come here, I will get 3. So basically I have to look at this thing and remember what is the longest common subword. It is that I comma j for which this value I have calculated is maximum. So in this case, this happens to be the maximum. So the answer is actually 3. right. So, it says that the longest common subword between bisect and secret is length 3, which we had also done by inspection. It is the word SEC. So, now in this we have not really calculated the word, we have only calculated this length. So, how do we get the word back, right? So, to read off the solution, first we find an entry which is maximum. So, we can keep track of it as we are going along, or we can go back and scan the table once to find the maximum, but we find the maximum here, right. Now, if it is the maximum, it has got to its value by adding 1 to its diagonal element. So, it added 1 to something here, which added 1 to something here, right. So, I should be able to walk down and find out all the entries that corresponded to that. So, I can walk down and then mark off these entries, and if I look at the corresponding entries on the two words, right, they will actually give me the words, right. So, these indices here, if I project it onto the column and the top row, then I actually find out that it is basically SEC, which is the witness. Now, there could have been another word of length 3, and that would have given me possibly a different, in this case there was only one witness, so I get SEC. But basically just computing the length is not a restriction, because from that we can read off the answer from the final thing. So, here is some simple implementation. These are, I mean, most dynamic programming problems are hard to set up, but once you have got it set up, then it is very easy to implement, because it is just a kind of nested loop through an array typically. So, here let us use a NumPy array. So, what we will say is that we will get the lengths m and n of the two words, and we want one, remember, which is m plus 1 times n plus 1. And because our base case is 0, it is convenient to set up this thing as a 0 length, zeros filled array. So, we use the zeros function of NumPy, and we get an m plus 1 by n plus 1 array of zeros. Now, I am going to keep track of the maximum length. So, this code does not tell you how to read off the answer, that you will have to figure out for yourself, but now it is just simple, right. I am doing it column by column, and I am doing it from m comma n down, right. So, I start with n minus 1, work down to 0, and I start with m minus 1, work down to 0, because remember the m and n column are implicitly 0, because I have already reset them to 0 here, right. And now I use the induction, right. If I have at the row and column the values are the same, then I add 1 to the value at the next row and the next column, the diagonal element. If they are not the same, I set it to 0, and depending on whatever I have calculated, right, I will update the max LCW, right. So, if the current LCW of this row column turns out to be more than the maximum I have seen so far, I update it, and finally I return the maximum, right. So, this is very straightforward. How long does this take? Well, brute force, if you remember, for every starting position, m times n starting positions, we have to do a potentially order n scan, so it is mn squared, whereas here we only have to fill up this table, which is m times n, m plus 1 times n plus 1, right, it is an order mn table. And how much time does it take us to fill up an entry? Well, we just have to look at the diagonal, right, so it is a constant amount of time. So, therefore, it is mn, because we have to just fill up this table of size mn, and each entry takes only constant amount of time. So, I have saved 1 power of n from my thing. So, I brought a cubic in some sense down to a quadratic. So, the longest common subword is not really the more interesting problem. The more interesting problem is a problem called the longest common subsequence. So, in a subsequence, we are not restricted to taking a segment which sits there, we can drop letters, right. So, for instance, with secret and secretary, I already have a maximum match, right, and so with bisect and trisect. But if I look at bisect and secret, earlier I said that you could only match SEC to SEC, but now if I allow you to drop letters, you can extend this to SEC T and then drop these two and go to T, right. So, you can actually move from a longest common subword of 3 to a longest common subsequence of 4. So, in a subsequence, as I am going left to right, I am allowed to delete some letters from either of the two until I find the longest match with deletions. Similarly, if I look at director and secretary, right, earlier we could only do 2, right, we could do EC or we could do RE, but now I can skip along and say, okay, ECTR, ECTR, right, or I can say RETR and RETR, right. So, by allowing some skipping, I get a longer subsequence. So, one way to think about this in terms of what we have is we are taking sections and adding them up, right. So, we have a longest common subword. So, let us look at bisect and secret, right. So, we have a longest common subword which matches these two, and then we have a separate common subword which matches these two, and they are in sequence, right. So, I can take this segment, which is the SEC, and then take the next non-zero entry bottom and right and combine these, and this will give me my longest common subsequence. But of course, this is not the useful way to calculate it, but just a way to think about it. The longest common subsequence consists of these blocks of things which are concatenated to each other. So why are we interested in this? Because this really has many applications. For example, in genetics, right, it is rarely the case that the gene sequences are identical, but there are large overlaps. So one way to check whether two species are similar is to see how much of an overlap there is in terms of this matching. Right? So you take and you allow yourself to drop some genes which appear in one and not the other, and see if the rest of the genome actually looks the same. So genetics is one application. Another application is more down to earth. So if you use a Unix or Linux system, there is a command called diff, which will take two text files and tell you how different they are. Now this is very useful, for instance, if you are editing some code or something, it will tell you which lines have changed. So what it does is it tries to compute the longest common subsequence between the lines of your text file. So it treats each line as a unit. So if you start editing your file by breaking lines, then it will think it's a different thing. But if you are editing your file by just staying within the same lines, it will tell you the maximum match between these two lines. Right? So diff actually uses a longest common subsequence calculation to tell you what is the maximum amount to which these two text files are the same and where the differences are. So it will say these two are different because here you have inserted this at line 5 and there you have deleted this at line 7 or something else. So it will give you some kind of a minimal way of taking one file and making it into another file. So there are several such applications where this longest common subsequence is used. So let's try to see how we will solve this using our inductive strategy. So as before, we have two strings of length m and n, and now we want to find in general for every position I comma j the longest common subsequence that starts at I in the first string and at j in the second string. So the first thing is that if the two positions are equal, right, then is it a good strategy to include this in our longest common subsequence? So we have ai plus 1 up to some am minus 1, and we have here bj plus 1 up to some bjn minus 1, right, bn minus 1. So now what we are saying is that these two are actually equal, right. So should I use that in my longest common subsequence? So I can think of a longest common subsequence as something that pairs up letters in the first one and the second one, right. So so I can pair up this, and then this might get paired up with something else, and that might get paired up with something else, and so on. But the pairing can never cross, right. I cannot pair up something earlier in u with something later in v, and then something later in u with something earlier in v, because that would not be a sequence, right. If I have, say, x comma y here, and if I have y comma x here, I cannot claim that y comma x is the same subsequence as x comma y. So this pairing must always be kind of non-crossing. So the question is, why is it a good strategy to do this? Perhaps there would have been a better thing, right, if I had allowed this to go and pair up with something to the right, or this to go and pair up with something to the right. So why not that? Well, supposing this was not the right solution, supposing there was a solution which goes there, right, but since ai is the very first thing here, right, it must go before anything that ai plus 1 touches. So I can always take this and move this back, right. So this is a bit like our greedy thing where we said you can take a solution and modify it so that it looks like a solution that I am giving you. So in this way, this is kind of a greedy strategy which says that if ai is equal to bj, include ai bj in your longest common subsequence. And the reason is, if ai could combine with something beyond bj, it can also combine with bj, and I will get the same solution. So the solution that you get by postponing your match for ai or postponing your match for bj cannot be any better than this, because that solution can be transformed to a solution which has this structure. So in other words, if ai is equal to bj, so in the case of the longest common subword, we said if ai is equal to bj, you just take 1 plus the rest. Here we are saying if it is equal to bj, you take 1 plus the rest again, right. So that part is the same. What if it is not equal, right? If it is not equal, then we can see that both of them cannot be in the same in the final sequence, because by the same logic, if I have ai bj, right, if this is part of my sequence, right, and I have not yet considered this, then ai must be matching up with something later. But now that's something later. If Bj is matching something, it must be, it cannot match up with AI, so it must be matching with something later. So then I have this crisscross, right? So if AI is in my solution, Bj cannot be. If Bj is in my solution, AI cannot be. It of course could be that neither of them is my solution. That's also okay, right? So the question is, what should I do, right? So I have to drop either AI or Bj and proceed. But since I don't know any better, I will do both, right? So I will solve it assuming that I drop Bj. So I will look at I comma j plus 1. And I will also solve it assuming I drop AI. So I look at I plus 1 comma j. I will look at both these subproblems. In one case I have omitted AI, in one case I have omitted Bj, and then I will decide which one of these is better, right? So I will take the maximum of these. So I am not ignoring anything, right? I am just doing all the subproblems that could contribute to this and taking the best one. So as with the longest common subword, the base case comes when one of the two strings becomes empty, then all the longest common subsequences become 0, right? So when I have either I comma n or m comma j, the longest common subsequence is going to be 0 just for the same reason as it was for the LCW case. So once again we have these subproblems of the form LCS I comma j for all I comma j. So we have these m plus 1 times n plus 1 table of values. But what is different now is the substructure, right? So substructure earlier, for a value here I only needed the diagonal, but now I need the value on the right and the value below, right? Because either it is equal and I go to I plus 1 j plus 1, or it is not equal and I have to take the maximum of these two. So I need all these three values to correctly evaluate I comma j for an arbitrary I and arbitrary. So everywhere I have these three contributors, right, which I have to keep track of. So that means that in order to solve this, I had better have solved all of these. In order to solve this, I had better have solved all of these. Otherwise, I am going to get into a situation where I will have to do some recursion. So if I am going to dynamic programming, I should make sure that when I reach a cell I comma j, I know what is to the right of it, what is below it, and what is diagonally below it. So as before, I can start here because there is nothing to the right and below. And again, for these things, I have a below, but I need these values, right? But because there is nothing to the right, it effectively means I must look below, and as we said, this is the base case because I am beyond the end of the string. So the last column is just zeros, right? Now here is the difference, right? So I get this is 1 because this t matches that t, all the others are 0, but the next column I will see a difference, right? So now what I see is that this e is not equal to this t. So LCW will say if E is not equal to T, then there is no common subword starting here, so I must quit. What LCS says is I can either discard the E or discard the T, right? If I discard the T, then I come here. Then I have ET with empty and that's 0. But if I discard the E, then I come here. I have a T matching a T, so I take the maximum of these two and I get a 1. Okay, and the same thing happens all the way up. If I look at E and C, it says, well, I could either discard the E or discard the C, right? And if I discard the C, then I am back to the ETT case, so I get this 1, and therefore the maximum of this and this is 1, right? So in all these cases here, I am taking, because they are not equal, because this, so here actually it is equal, right? But here I am getting 1 plus 0 is 1, right? Here I am getting maximum of this is 1. So in each case, it is 1 because either it is not equal and the maximum of the two subproblems is 1, or it is equal in the specific case of E and I get 1 plus 0 is 1. Okay. So I keep going like this, and now here for the first time I see, when we see the C here, remember that this is where the longest common subword initially ended. It is 2 because it is a match plus 1, and this 1 is basically coming from here, right? So there is a match further on. What it's saying is that I have a match here and there is some match further on with some gaps perhaps. So therefore the total match starting at this point is 1 plus that match which was 1. So 1 plus 1, 2. Okay. And going backwards again I get a 3 and then I get a 4, right? And unlike the longest common subword thing, this will always be the maximum, because if I start at 0 comma 0, I can always, if the supposing the maximum happens at, in this case, at actually comes at 2 comma 0, right, because it's SEC, so it is at position 2 in bisect and position 0 in secret. But I can think of it as having dropped the first two letters in bisect, right? So therefore, even from the beginning there is a substring of length, subsequence of length 2 by just dropping the first two letters. So the maximum for LCS is actually going to happen at 0 comma 0 always, because it accumulates all the LCSs to its right. It's not like LCW which must start there, right? So we get that. Now you can ask the same question, how do I recover? Well, I look at this, now I know that this is my maximum, but where do I actually accumulate letters in my longest common subsequence? Wherever I have a match and I go diagonally, right? So I have to basically track how did this entry become 1. So this entry became 1 because of 0 and 1. But how did this entry become 2? Well, this entry became 2 because I had a 1 here and then I added 1 to it. So for each entry that I made in my table, I know whether I got it from the diagonal entry because there was a match, or whether I got it from the maximum of the table entries below and to the right because it was not a match. So wherever there is a match, it contributes. So basically I trace back this entire computation by just keeping track at every square of which of the two cases in my inductive definition I used. Did I use the max or did I use the +1? And if I use the +1, then this is good, right? So I find out all these positions where I did a +1, and this gives me 4 to 3, 3 to 2, 2 to 1 and 1 to 0, right? See, these are the 4 places. So this, if I now go back and map those 4 places there, I get the corresponding segments in my word which contribute to this LCS. So once again, by doing a little bit of extra work after I do the length calculation, I can actually recover a longest common subsequence. So finding the length is actually enough, and the length is the one that is easier to define inductively. So you first calculate the length inductively, and then you analyze how that inductive definition unrolled in order to calculate the actual word, right? So again, the implementation is quite straightforward. It's even more straightforward than LCW because I don't have to keep this maximum, right? So I just set up these this array with zeros, and I just run through this, and I use the 2 inductive cases, right? So either I do 1 plus the diagonal, or I do the maximum of the 2 things which are 1 below and 1 to the right, right? So this is the easy thing, and finally I return the value at 0, 0. So just like for LCW, LCS also basically fills up this m times n table, right? And each entry takes constant time. So this is also something which takes time proportional to m times n.